Hi, everyone. I'm Danica, and we have Dr. John Donohue with us today. And just as people are joining, maybe you could put in the chat, are you a student? Are you with a startup? Are you in academia? Are you in industry? Maybe you're a professional. Maybe you're all of those things. Maybe you're a high school student and one of your parents said, join this call, it's interesting. I'm just curious to see where everyone's from. Industry, academia. I wonder what I am. John, you're at the Institute. Are you a student and an academic?
I'm a part researcher, part academic, part teaching. It's a little bit of a mix, but I am at the academic level, yeah.
Awesome. Oh, and hi, Esperanza from Madrid. Anna from Argentina. Okay, hey, that's great. Individual lifelong learner. I love that. I love that. You know, awesome. We're in that mindset now. So I love to see people embracing it. Yeah, maybe put where in the world you are. I'm an American and Canadian in Montreal. How about you, John?
I'm coming to you from Waterloo, also Canadian from Chatham, Ontario.
If anyone's in England, there's another Chatham here.
Yeah, we got one.
Wow, how great. So everyone's joining, and just going to kick off with a couple house rules. So thank you, first of all. We are going to be using the chat, and we want to make this interactive. So some of y'all are doing it. Don't be shy. If you want to just quietly private message us, that's okay. We've got a few people from Association Quantum helping to manage the chat. So if you're a little bit shy, that's okay. We still want to hear from you. There's lots of ways to connect and communicate, including, if you're not aware, Association Quantum is on lots of social platforms and they do a newsletter. So we'd love for you to sign up, because what we're trying to do is build this community. And that's you. I mean, we're fascinating people, but if it was just me and John having a conversation, we might just have a coffee together. This is a community event, and actually you're part of that community. So I'd say join and bring your friends to the next one. Other house rules. Yeah, you have to bring your own beverage. Although in future, when we can open things up safely, we will be doing some more in-person events around the world. And that may be you organizing them. So do stay in touch, because it's a real sharing community. We have people from different parts of the world and different aspects of life. And that's what we're doing. We're bringing together people to share and spread quantum knowledge, to find creative ways to harness this technology. Maybe there's researchers, and they also want to be able to commercialize the tech. Maybe you're in industry and you're saying, wow, this is something that I need to learn about. I really want to be able to use this capability in a new way, and you need that research to help. Or maybe you're a startup saying, okay, I can get some lift off. I have this idea, but I need the deep research and I need the industry. So that's what our community is all about. So welcome. Also, I want to thank you for joining today. We postponed from yesterday because it was pretty important. There was a day of action around the world to recognize that Black Lives Matter. And for our community, we're really about inclusion. So we did postpone to today so that some of us could participate, you all could participate, because it's important. And what we're trying to build is a new future, which is really the theme of this call. I mean, specifically about quantum information. And so our new future includes inclusion and diversity. And when I say diversity, I mean things that are important, like things that we see, race, gender, various abilities, but actually also diversity of thought. So if you know someone who is a visual artist, bring them to the next call, get them to join this association, because you know what, in the new world, visual artists can represent data in a beautiful way. So there is a lot of possibility and opportunity, and that's part of what we're going to talk about today. There's going to be a survey sent out at the end, and this call is being recorded. And being part of our community and newsletter, you will get links to this recording, our poll, to help us know what you want to hear. And the next call will be on finance. So we'll have a little screen on that and we'll send you out something. So today, what we're talking about is quantum information science. I think a lot of times back in the day, there was a TV show called Quantum Leap, but we tend to think of like quantum computing as a subset. There's so much more. Actually, I didn't know. Quantum communication, quantum metrology, quantum sensors. I'm glad John's here because he's going to take us through this. I mean, I joined because I wanted to learn as well. And now over to John. So he is from the Institute for Quantum Computing, and that's a research institute at the University of Waterloo, which is in Canada and world renowned for its phenomenal deep research. His role is scientific outreach manager. So he's here to really oversee educational workshops. He does teacher networks, public lectures, even museum exhibits. So it's a pretty cool way to take this really deep tech and bring it to the world. He did his PhD and postdoc in Waterloo and in Germany. So I think there were a couple of people in Germany. And he studied quantum optics, ultra-fast measurement, and entanglement. So John, I'm 6 feet tall, and my 12-year-old is 6 feet tall, so that's ultra-fast growing. I'm gonna hit you up for information on that later. And then we would just really want you to all throughout, communicate, ask questions. There will be a couple breaks and a discussion at the end for Q&A. So welcome, and over to you, John.
All right, thank you very much for that introduction, Danica, and thank you very much for having me today. A day late, but I'm very glad that we were able to take that bit of a reprieve and, come back again at it today. So, as Danica mentioned, my name's John Donohue. I'm the Scientific Outreach Manager at the Institute for Quantum Computing. Before that, I was a research scientist. So I studied quantum optics, which is the study of how light works at like kind of the individual photon level and how it interacts with other things like different kinds of crystals, different kinds of atoms. Particularly, I was interested in like how we could make individual photons of light and how we could measure them in very specific ways, how we could create large entangled states of photons. And I guess I really got, if you were to tell like the 16-year-old me that that's what I would have been doing, in my 20s, I would have been very surprised. I was not expecting to become a physicist. When I was young, I was really more into movies. I was really more into like journalism, that kind of approach. But then when I was in school, spent a bit of time in a laser lab and just fell in love with it. Fell in love with kind of the depth of the mathematics behind it. Fell in love with just playing around with kind of like Lego sets of lasers and just, having fun in that regard. I wasn't so much into the computing aspects, but when I found out that it was like something that you could connect to computer science, something you could connect to information technology, it just kind of opened up the world beyond there. So I'll just share the screen now. So as Danica mentioned, I'm coming from the Institute for Quantum Computing. So we're a research institute at the University of Waterloo. We've been around since 2002, which is a lifetime ago in terms of quantum information. So really kind of the field of quantum information started in the early 1980s and kind of blew up in the late 1990s with especially with the proposal of Shor's factoring algorithm, which kind of lit a fire underneath the community. So IQC was founded in 2002, kind of just as things were starting to ramp up in the research community. Right now, we've gone from a very, very small group in the middle of a hallway somewhere to about 300 researchers in over 30 different research groups from 7 different departments, kind of tackling quantum information challenges from a variety of angles. So there's people like me with a background in physics who study it. Even from there, you're talking about a variety of angles. You're talking about people who study photonics. You're talking about people who study atom interactions. You're talking about people who study neutrons. You're talking about a whole bunch of different angles there. In addition, you have people working on it from a chemistry perspective, from a mathematical perspective, from a computer science perspective, from an electrical engineering perspective, from a clean room and nanotechnology perspective. There's a whole bunch of different angles and a whole bunch of different viewpoints that need to be taken into account when building these kinds of technologies. So what I'm here today to talk about is what I'm going to call quantum beyond computing. So what I mean by this, so I'm going to be talking about what I find is that quantum computing, when we talk about these kind of things today, computing takes up all the oxygen. People talk a lot about quantum computing. If you Google quantum computing, you'll see about 17,000 different articles, all giving conflicting information, but all talking about how cool this quantum computing paradigm is. What I want to talk about today is that there are other things happening in quantum science other than just computing. But what I don't mean are a few of these things. So for one, quantum is a very, very, very old topic. I'm not here to talk about all of quantum beyond computing. It's a very, very broad topic. And not everything that happens in quantum physics is necessarily new. Like the idea of quantum physics dates back to the late 1800s. Kind of the initial philosophical arguments of quantum mechanics date back to, you know, the 1910s, 1920s. And after that point, it was no longer really considered to be that, you know, radical of a theory per se. By the mid 1950s and especially up into the 70s, we were already building technologies that you couldn't even think about using without using quantum mechanics. Things like MRI machines are entirely a quantum mechanical phenomenon. Things like the laser, you can't even imagine really, you know, you can't write down what a laser does unless you're also thinking about it from a quantum mechanical perspective. Things like semiconductor technologies and LEDs, these are all based on kind of a quantum mechanical theory. So quantum is a very, very broad topic, and it's not that much of a new topic either. It has been explored. I'm also not going to be talking about this kind of stuff when I'm talking about quantum beyond computing. In kind of parallel with the hype of quantum, we've also seen kind of the word quantum just associated with a lot of stuff, and especially in the last couple decades. So as much as I'd love to go off on the quantum RV, and if for people joining from Toronto, I hear a lot of really, really good things about quantum coffee. Not here to talk about quantum marketing per se either. If I were to give a very specific title to what I'm talking about, I would say I'm talking about quantum information beyond computing. So quantum information, like I said, quantum is not a new topic, but quantum information is a relatively young topic. And that's kind of taking the ideas of quantum mechanics and merging them with a stream of thought that kind of evolved in parallel to quantum mechanics throughout the 20th century. And that's information theory. That's where you treat information, you know, bits floating around, notes that you write down, anything that can be used to gain information, you treat it as a physical property. You treat information as physical, as something that has to obey the laws of physics in a certain sense, laws like entropy. Thinking about how that changes when you introduce ideas from quantum mechanics is a relatively new field of study. And one of the biggest things that has come out of that is the field of quantum computing. But as we kind of formalize those ideas and other new technologies kind of pop up alongside. So first off, before we talk about too much about these other technologies, we are coming at it from, I imagine a lot of the audience has seen talks about quantum computing before. So let's dive a bit into the guts of quantum computing first, and then talk about how we use those same guts, that same magic in technologies like quantum communication and in technologies like quantum sensing and metrology. So before we talk about quantum information, before we talk about quantum computing, I should just quickly define what I mean by a computer in this context. So a computer is an information processor. Any computer I can think of in this way, I have some input, which doesn't matter if it's words that I type on a keyboard, doesn't matter if it's a Google image search, I can break that down into a binary string of zeros and ones. That's my input. It goes into a black box. That black box shakes up those zeros and ones and spits out some useful output. I type in a Google image search, it gives me the image I want. I type in 3 times 3, it tells me 9. I give it some input that I don't know what to do with. The computer shakes it up and gives me some output that I actually want. A quantum computer is really, you can think about it as in the exact same way. I'm going to give it some classical input, which is a bunch of zeros and ones. It's going to go into this magic black box, and I'm going to get some useful output out. I still know the input I'm giving it, and the output I get better be something that I can understand. The key difference is what's allowed to happen in that box. In the classical computer, it has to obey the laws of classical information processing. So certain problems are very, very easy for a classical computer to solve. For example, multiplication is a very, very easy problem for a classical computer to solve. It can very, very easily tell me that, 3 times 5 equals 15. But it might have a harder time doing that same problem in reverse, asking for the factors of a number. So tell me that 15 equals 3 times 5. Obviously, 15 is not a very hard example, but if I go to a much, much larger number, this becomes a very, very difficult problem for a classical computer, even as multiplication remains a very, very easy problem. The quantum computer, still the same idea. I give it some input, I give it some output, I get some output, but the rules that the box obeys in the middle, those change drastically. I'm allowed to use extra tools. I'm allowed to use extra kinds of operations. And by using those, some problems get easier. Some problems include factoring, for example. So this is the famous Shor's algorithm of 1996. If I think about how hard it is to find the factors of a number, classically, it's an exponentially hard problem. As the number of digits grows, the hardness of the problem grows exponentially with the number of digits in the number. Quantumly, it grows something like quadratically. So it's still a hard-ish problem, but it's, well, actually, when we're talking quadratic, it's what computer scientists would mostly consider a pretty easy problem. So something that's very, very hard for classical computers, by using these kind of quantum properties, becomes much easier. Maybe the original idea behind quantum computers was to simulate quantum physics. So if I want to run a simulation of quantum physics, say I want to get an idea of what would happen if I were to build a particle accelerator, I'm going to need to understand the quantum mechanics of those interactions in order to program a computer to tell it, figure out what might happen here, and then we'll actually test it with our big particle accelerator. In order for the classical computer to do that, I need to basically teach that classical computer quantum physics. So I need to program quantum physics into that computer. Classical computers, they don't understand quantum physics naturally. I need to tell them all the rules. A quantum computer, on the other hand, I'm waving my hands around very, very widely here, but they kind of already understand the rules of quantum mechanics, so my quantum computer can simulate other quantum systems much more efficiently, which has uses in, for example, simulating how different kinds of materials might work, simulating different high energy physics problems, simulating how proteins fold. These are all things that a quantum computer could be useful for. If you want to see a whole bunch of computer science arguments for this, I recommend checking out the Quantum Algorithm Zoo. They have a lot more information about exactly what kinds of algorithms and exactly what kinds of speed ups a quantum computer might be useful for. So what's the magic? What makes that happen? So I kind of said that, okay, what the rules that happen inside the box are differently, but why are the rules different inside that box? If you've heard anything about quantum computing, what you've probably heard about is quantum bits. So a bit is the unit of information. A bit can take a value 0 or 1. And I can build any kind of information by breaking it down into these bits. So for example, an LED is an example of something that can work like a bit. It's either off or it's on. It's 0 or it's 1. Like a light switch, it's 0 or it's 1. Like a coin, it's heads or it's tails, which I can call 0 and 1 if I want to. A qubit works in the exact same way. So a qubit is a quantum bit. It's a bit based on a quantum system. An example is, say, the spin of an electron. So an electron has a magnetic field. Think about it like a little tiny bar magnet. And I can flip that electric field by sending energy to it. So if the electric field is pointing north-south, I'm going to call that spin up. I'm going to call that 0. If the magnetic field is south-north, then I'm going to call that spin down. That's going to be my bit 1. So I can encode a bit into the magnetic field of an electron this way. However, because it's a quantum bit, I can also put it into a superposition state. So a superposition state is where it kind of has a little bit of a component that spin up and a little bit of a component that spin down. It's often called being both spin up and spin down at the same time, so both 0 and 1 at the same time. These kind of superposition states don't really exist classically. So on a very surface level, by having the superpositions, we kind of have more things that we can do with our quantum bits. But the actual story is a little bit more complicated than that. So let's take a look at our superposition state, which I'm going to call plus. And this plus state we write as 0 plus 1. Don't think of it as 0 plus 1 equals 1. Think about it as it's a little bit 0 and it's a little bit 1. It's a superposition of 0 and 1 at the same time. Now then, if I were to ask the question, is the particle 0 or 1 from like a purely philosophical standpoint, I have to say, well, the particle is both 0 and 1 at the same time. But there's an important caveat there, and that is that when I measure the bit, when I ask the bit the question, are you 0 or are you 1, it's going to tell me it's either 0 or 1 randomly. I don't have any control over what it is. It's like the universe flips a coin and tells me it's 0 or 1. Let's go one step deeper. Because the important thing there was not that it was random. The important thing there was that I asked it the question, are you 0 or are you 1? there are many different questions that I can ask a qubit. So in this case, I asked my superposition state plus, are you 0 or are you 1? And it told me 0 or 1 randomly. This is what we're going to call the measurement context. It finds which question I asked the photon, or sorry, the electron. I could have also asked the question, are you the state plus? In which case it would have told me with 100% certainty, yes, I'm plus. Similarly, I can almost kind of reverse that thing like an Ouroboros onto itself. I can say that if I had the electron state 0, I could think about that as a superposition of different superposition states. Now I have to say that the electron is in the superposition of the superposition state, so it's both the plus superposition and the minus superposition at the same time. And when I ask the question, are you plus or are you minus, I'm going to get a random answer of plus or minus. So this is kind of the duality there, where I have these superposition states, but it depends on how I'm thinking about it, whether or not I think about it as a superposition or not. And whether or not I think about it as superposition depends on which questions I ask. It depends on the context of the measurement that I make. So why does quantum computing work? Well, it's a bit of a mix of all these different things. So it's a mixture of the fact that we can have these superposition states. It's a mixture of the fact that we have different measurement contexts that we can make, that we have kind of a more complex selection of measurements that we can make on our quantum states, as well as something called entanglement, which we'll dive into a bit later on, which basically when we get multiple qubits together, and we have many of them in a row, we can get a very, very complex quantum state as they kind of all become correlated with each other. So these are the different properties that we make use of for quantum computation, but are they useful only for computation? Or are there other kinds of information processing tasks that can benefit from this approach? And we're going to dive into some of those now. So we're going to go to part 2 of our talk, which is quantum communication. So I'm going to start off by talking about quantum communication from the perspective of the quantum threat, which I'm using scare quotes here because if you've seen some media coverage, you've probably heard some talk about how eventually we're going to have a quantum computer and it's going to destroy the entire security of the internet, and we're all going to go back to living in caves or something. Might have come up before if you've done some Googling around. That's the terminology. It's a little extra more scary than it needs to be, but I'm going to stick with it for now in those ever important quotations. So the idea of the quantum threat comes from how we actually get security over the internet today, and that's through something called public key encryption. The basic idea of that is to keep information secret by using something called a one-way function. That's something that's easy to do one way and difficult to do the other way around. So I'll use the example of an egg. If I have an egg in a frying pan, it's pretty easy for me to make a fried egg. I'm not a great chef by any means, but I can fry up a mean egg. So, however, if you ask me to do the reverse problem, give me a fried egg in a frying pan and ask me to build the egg back, that's a very, very difficult problem to do. Technically speaking, it's possible. From a very information theoretic, perspective. I'm not sure if any chemist has done it. I wouldn't be surprised if so. But it's something that is technically possible. We can abstract this away to think about kind of a more from a computer science perspective. So let's say we have a function f of x, and we want, so that's going to be like some kind of code. I'm given an input x, and I get an output f of x. And my input is x, my output is the value of the function f of x. If I have x, it might be very, very easy for me to get f of x out. It might be very, very easy for me to scramble up x in some way that I get this function out. However, unless you know some kind of extra information, it might be very difficult to then take that f of x and get the input value x out. So think about x as my secret, and I want to send that to someone who can get that secret out. I'm going to encode that as f of x. And because of how they've set things up, they have a secret that allows them to get x out easily. That secret could be, for example, the factors of a large number that they gave to me. So we'll see where we're going there. But however, if someone doesn't have that secret, if some black hat hacker does not have that secret value, they won't be able to get x out, and my information will be secure. Or it might be a very, very difficult problem for them to get x out. If they had, 100 years and the most powerful supercomputer in the world, they could make it happen. But practically, it's not going to happen. The problem is that in order to devise these kinds of questions, we're thinking about things from the perspective of a classical computer. We're thinking about the laws of classical computation. If I have a perfect quantum computer, that might not be the case. The perfect quantum computer might be able to crack that code, to reverse that one-way function in a way that might not be super difficult. An example of this is factoring. So one of the most commonly used encryption algorithms is RSA. The guts of RSA are based on the fact that factoring is a difficult problem. So if I had a perfect quantum computer, then I could crack RSA. I want to be clear that in order to have a perfect quantum computer that could crack RSA, we would need a fault-tolerant quantum computer with something like 1 million logical qubits. I won't get into exactly what all that means, but suffice to say, we're not at the point where we really have one logical qubit yet. So we're talking about something very, very far in the future, but something that is possible. So is it something we need to worry about right now as people? No. But if we're working in industries or working in government where security is, really, really, really paramount, it is something to at least be aware of. All right, yeah, so public key cryptography is based on these kind of one-way functions, and they classify the one-way functions depending on their computational difficulty. And this computational difficulty can differ between quantum and classical methods. So there are so thankfully where quantum physics kind of breaks something, quantum physics also tends to introduce a solution. So there are two solutions, two different kind of streams of thought, two complementary solutions, but nonetheless kind of two different specializations into thinking about how we can get security back. So the one that I'm not going to talk about really is post-quantum cryptography. The idea there is to think of new kinds of one-way functions. So instead of f of x, think of g of x, where it's still pretty easy to get from x to g of x, but even if I had a quantum computer, design an algorithm that a quantum computer would still have a hard time cracking as the reversible one. So this is a little easier said than done. These algorithms that we use today are chosen because they are very, very efficient. There are algorithms out there that people are pretty sure would be very, very difficult for a quantum computer to solve, but these proofs are not, even the proof for why factoring is a hard problem classically is not rock solid. It's just, we would assume that if we were to have something that would break it, we would have found it by now because people have been studying it for decades. So it's very, very hard to rigorously prove something in this field, but it's very, very doable to come up with convincing arguments. One of the problems is that the algorithms used now are designed to be very, very efficient. The algorithms that might be useful for post-quantum cryptography are not necessarily as efficient to encrypt and decrypt with. They might need a lot more bits as overhead. They might take a lot longer to actually package up your information. And as well, a lot of the fixes that need to go in there are at the hardware level. It's not always something like downloading a patch over the internet. The other way to think about it is kind of that, so that's kind of the more cryptography, the more computer sciencey way to think about solutions to it. The more physicsy way to think about it is kind of to step back a step. So when we're talking about these one-way functions, we're talking about something that's asymmetric, something that's very easy to do one way, very difficult to do the other way. So kind of the amount of information that each person needs, the encryptor and the decryptor, is very unbalanced. It's very asymmetric. As the encryptor, I need very little information to encrypt. The decryptor needs a lot of information to decrypt. We can go back instead to kind of like an old school method of cryptography, which is symmetric keys, which is where the encryptor and the decryptor have exactly the same information. Turns out this can be perfectly secure, but it has one very, very key problem, which is how to actually share out those secrets in the first place. So the kind of strategy we're going to use there was we're going to actually use that quantum magic to distribute those shared secrets. So symmetric key cryptography, if you've ever done like any kind of basic cryptography, like worksheets, or ever kind of like exchange notes in class, you're probably pretty familiar with how this is going to work. So we have two people, we're going to call them Alice and Bob. And Alice wants to send a message over to Bob. Alice doesn't want someone in the middle to be able to read her message. So what they're going to do is first they're going to agree on what they're going to call a key. And that key is just a string of random zeros and ones. It doesn't matter what the key is. The only thing that matters is that Alice and Bob both agree on what it is. So Alice is going to take her message, which, if I remember correctly, is the ASCII character H in this case. She's going to add her message to the key, and she's going to get what's called the encrypted message. If I look at the encrypted message and I don't know what the key is, I have no way of telling what it could be. I know it's 8 bits long, so it could be any possible combination of 8 bits because I don't know what that key is. However, because Bob has the key, he can unscramble the message in the exact same, unscramble the encrypted message and get the original message out, which is perfect. So in this scenario, assuming that they keep their key completely secret, this is perfectly 100% secure. The problem is, of course, how do they share the key in the first place? Those public key cryptography schemes from before, the way that I encrypt my message to the bank, that's perfectly public knowledge. As long as the bank keeps it secret, it's safe. In this case, both Alice and Bob need the same secret, and they need to distribute that very securely. So you could think a Cold War style, you know, send someone in a plane with a briefcase full of codes attached to their wrist, which, I mean, I think as far as I know, some people still do that. But, you know, quantum mechanics offers a slightly different solution based on these kind of quantum phenomena. So the idea here is Alice and Bob, instead of sharing the key using classical messages by, you know, sending electricity down a wire, they're going to distribute this key using entanglement. I'm going to use the, I'm going to go on. So oftentimes people have heard of this before. Probably, if they've heard of it before, we've probably seen it, that it is Alice sends photons to Bob. It's called the BB84 protocol. I'm going to use the entangled version, which is the Eckert 92 protocol. And the idea here is that Alice and Bob are going to measure photons from an entangled source. The entangled source is kind of this like black-gray circle in the center of the screen there. It's going to send out photon after photon, and those photons are entangled with each other. They're entangled in such a way that if Alice and Bob measure them in the same way, they always agree on what the answer is. So, as we mentioned before, there are different questions I can ask my photons. I can ask them, are you 0 or are you 1? And if Alice and Bob both ask the question, are you 0 or are you 1? Their answers will always agree. If they instead ask the question, are you the positive or the negative superposition? If they both ask the same question, they're also going to always agree. However, if Alice and Bob ask different questions, say Alice asked the question, are you 0 or 1? Bob asked the question, are you the positive or negative superposition? They get some random noise, which is fine, because if they just, at the end of the day, say what they measured, they don't say the result, they just say what they measured, then they can kind of filter out and only take the answers where they agree. So, okay, this is one way they can kind of share and then generate something that they're positive. It is completely random what it is. Whenever you measure a superposition state, you get a random answer out. So you can actually certify the randomness of this. So you get a completely random string out, and they both agree on what that random string is. So where does this, it's pretty easy to just have them share a random string. Where does the security come from? Well, when you measure a quantum state, you change the quantum state. Let's think about it from Heisenberg's uncertainty principle. So Heisenberg's uncertainty principle states that the more I know about position, the less I know about momentum and the reverse. Another way to think about this is that a position state is really just a superposition of a whole bunch of different momentum states. So if I send you information encoded in the position, then you must know nothing about the momentum. However, if someone in the middle measures the momentum, if someone asks the photon in the middle, what is your momentum? Then they're going to disturb the position of that photon, because you now suddenly know a lot about the momentum, so the position must become much more uncertain. In the same way, if someone sends me a message encoded as a 0 or a 1, and I ask the question, are you plus or are you minus? I'm going to disturb its 0-1-ness. I'm going to introduce uncertainty to whether or not it was 0 or 1. From a kind of bit perspective, I'm going to introduce errors into the string. So if these eavesdroppers come in and start measuring the photons in between the source and Alice and Bob, they're going to introduce errors into the secret key that Alice and Bob generate. And as they keep generating these, they can do some kind of error checking just to get an idea of what their error rate is. And if it's above a certain threshold, then if it's below a certain threshold, they can guarantee that an eavesdropper was not present. If it's above a certain threshold, well, they have to throw out their key because someone might have been listening in. So this is a way that they can detect an intruder. So if an intruder comes in, they can kind of destroy the key by measuring things, and then you just lose the key. However, if we find that there is certifiably no intruder, then we know that, hey, we can use this key for whatever we want afterwards. We have this key that is kind of has a quantum stamp of approval, a quantum stamp of security. Yeah, so sometimes you don't get a key, but whatever key you get, you know that you can trust. So that's kind of the idea of quantum key distribution. So there's a couple different things we need here. We need, we're going to use photons always in this case. There's a lot of different quantum systems, but we're going to use photons because we want something that travels very well. We want something that can travel a very long distance and maintain its superpositions over a long distance. And there's a few different challenges when we start actually trying to do this in a lab. So challenge number one is distance. So if I want to do this, I want to do this because I want two very, very distant parties to communicate with each other. It's not really useful if we're kind of doing this if we're both in the same room. So we need some way for photons to get from Alice to Bob. And we don't want to lose too many photons in the middle because something I didn't mention there is we really need to send exactly one photon of light at a time. So we can't do the classic trick of just boosting the signal with some kind of amplifier like we do in classical communications. So optical fiber works really, really well for this. The same way that we can couple light signals like telecommunication signals through optical fiber, single photons can also travel through optical fiber. Works great. We can use almost all the same tools except for amplification that you use in classical telecommunication, but you're still limited in exactly how long you can transmit information for. You're limited to about 400 kilometers given current detector technology before you just lose too many photons to make it usable. Another option is to go to free space instead. So really talk about telescopes and like basically shooting photons through the sky. The way a lot of people are working on that now is through the use of satellites in low Earth orbit. So what I'm literally going to do is I'm going to take a telescope on the ground, I'm going to shoot a photon into space. That it's going to be collected by a satellite in space. Someone else is going to then shoot a photon from the ground at the same exact satellite. The satellite's going to collect that information and use that to distribute the key. This is what we would call an uplink satellite. And as insane as that sounds, it kind of works. Like it has the potential of working. You might think, okay, what about clouds? You know, if we're worried about absorption and photons being lost in fiber, why aren't we worried about them being lost in space? I mean, as long as you have a relatively clear day, the atmosphere is really only like yay thick on the grand scheme of things. Once you get through that lower layer of atmosphere, you're almost in the vacuum. Photons don't get absorbed if there's nothing there to absorb them. So far the world record for this was by a group out of China, and they used a satellite to set up a quantum communication between Vienna, so between Austria and China, between Beijing and Vienna, roughly. There is also a Canadian mission right now called the Quantum Encryption Science Satellite, being led by Thomas Yanovine's group out of the Institute for Quantum Computing. They're looking at sending up a satellite into space through partnership with the Canadian Space Agency and some industrial partners. And yeah, that's something that's, so it's using what's called a microsatellite, which is about as big as a suitcase. So something about that size is going to go up into space, and people in Canada and around the world are going to be shooting photons at it to send these quantum keys over very, very long distances. So that's challenge number one. Challenge number two is the equipment. So we're only as secure as our equipment is in this protocol. Think about it this way: we have these public key encryption protocols right now, and they work. But if I leave my password on a Post-it note on my screen, I'm not exactly going to have a high security. So it's only as secure as I allow it to be. The problem with a lot of encryption protocols, the base problem is not usually with the encryption. It's usually with the users. It's usually with different ways that we can use to kind of interfere with how the signals are processed, like how we send that information, how people use that information, rather than the mathematical problem of the encryption. So that's almost always the real problem. So an example of how someone could hack QKD would be if you were to control Alice or Bob's detector. So Alice and Bob, in order to make this work, have to have something that detects a single photon. So something that takes a photon in, gives an electric pulse out that a computer can understand. However, if I am able to take control of Bob's detector, so I'm able to take control and control what Bob sees, so that it doesn't depend on the photon, but does depend on what I do to it, I can mess with the security of their protocol and end up getting their key. This is a detector control kind of attack, and it turns out to not be that difficult to do. If you send in a whole bunch of other photons into Bob's detector, you can control what his detectors do. There are different patches you can do to kind of prevent this attack from happening, something called the decoy state protocol. You can have something that detects when someone is sending lead into your detector, but this is kind of like, putting band-aids on a sinking ship. You need, is there a kind of a more fundamental way to get this security back? Thankfully, once again, there are ways to do it, and this is where we kind of bring in some ideas from entanglement. So this is the idea of device-independent QKD. So we're going to use entanglement to remove the assumptions on the devices. So last time, Alice and Bob were able to ask one of two different questions. Are you 0 or 1? Are you positive or negative superposition? In device-independent QKD, we're going to add a third question in there, and that question is, are you entangled? So Alice and Bob, whenever they ask the question 0, 1, or plus minus, they'll use that to generate their key. Whenever they ask the question, are you entangled, they're going to play a little game. They're going to play a little game called the bell game. Basically, what they're going to do there is they're going to collect data, and that data is going to tell them whether or not the photon source is actually sending out something that is entangled. You can do this using different kinds of inequalities, different kinds of mathematical tricks, where basically you're testing how strong the quantum correlations are between Alice and Bob's photons. So a hacker can take control of Alice's device. A hacker can control what Alice measures and how her detectors go off, can take control of all of that. And another hacker can independently take control over everything that Bob does. And they can control it, they can plan a strategy in advance such that they always agree whenever they measure 0, 1, or plus minus. But because they're building that strategy based on classical correlations, they aren't able to mimic the quantum correlations that come out of entanglement. They can only do that if they're not there, basically. They can only do that if they're violating the laws of quantum mechanics. So even if they manage to make Alice and Bob agree on what's 0, what's 1, what's plus, and what's minus, they're going to fail that entanglement test. So if Alice and Bob measure A, that their bits 0, 1 agree, their plus minus bits agree, and that they pass the entanglement test, they can be sure that there's no hacker also controlling their device. Even if they let the hacker take control of their device, they can be sure that their bit string is secure as long as they pass that entanglement test. And assuming that the hacker isn't also looking at the output coming out. That part's important. as long as they assume that where they're reading the output from is secure, then they can assume that even if the hacker controls the device in the middle, they're okay. So there's, this is a little harder, even harder said than done. Not only do you need to have that entangled source and that entanglement test, which is relatively standard now, you need to also be able to remove all other possible loopholes. So that means you need incredibly sensitive detectors. You need to make sure that the choices of measurements are made in such a way that a signal traveling at the speed of light from Alice to Bob couldn't have influenced that measurement, or else the hackers could have collaborated on their strategy. So you need to have them very, very far away with very fast equipment, which sounds tough, but has been done. So in 2015, there were a slew of experiments shown by people at NIST and in Vienna and different places around the world where they were able to violate these bell games in a way that closed all of these possible loopholes. So this kind of ingredient has been shown before. It's still pretty far away from being able to be used as a practical tool in device-independent quantum key distribution. That being said, it has started to be used by folks at NIST to generate kind of very, very certifiably secure strings of random bits. All right, so when we're talking about quantum communication, we have these same quantum information ideas that we use in quantum computing, things like measurement context, things like entanglement, and we can use them for secure communication. If we take a quantum lens on crypto systems for post-quantum cryptography, that's what's going to be needed for a lot of this kind of future-proof security. And if we want to take a physics lens approach to it, the multiple ways that a quantum state can be measured can be harnessed for QKD and quantum key distribution. Whew. So that's what I have to say about quantum communication. If there are any questions about this, I could take a quick break before moving on to sensors.
We did have some questions and discussion in the chat.
Awesome.
And, you know, I'm going to try to get my kids to unfry an egg. Awesome.
Keep them busy for a while.
Hey, it's homeschooling. Ping, you had a question. I think Alexandra and some other people answered. I'm just going to give a moment if anybody has questions at this point or comments. Applause. Yay.
Yeah, cool.
Awesome.
Yeah, so I see one question. Yeah, I guess how do we know if the process data is accurate? So what we're going to do is we're going to kind of sacrifice some of the bits. So they build up this big string of bits that they think agree with each other, and they're going to sacrifice some of them. So they're going to say, this is not exactly how it works, but one way to start thinking about it is I'm going to give away the first half of the bits, and we're going to see if those match. If they match, well, we can be pretty sure that the second half of the bits also match. In reality, what we're going to do is we're going to actually start looking at things like the parity of the bits. So we're going to divide the bit string into, say, groups of 3 bits. And I'm going to add each of those 3 bits together. So my first 3 bits are 0, 1, and 0. So the sum of them is 1. The next ones are 1, 1, and 0. So, you know, 1 plus 1 is 2, but we're going to drop remainders because we're doing binary. So we're going to call that 0. And we're going to see if that kind of parity works for the entire bit string. If we're sure that each group of bits has the right parity, we can be pretty sure that everything else, that each thing in those groups of bits also agree. So then we just drop 1 bit from each group and we get our security back perfectly. So yeah, that's kind of the idea. We sacrifice some information, so we give up some of the key to make sure that the rest of the key is accurate.
So there's a question from Alexandra. How do we know the information got scrambled due to eavesdropping or due to noise from environment or other factors?
We don't know. There's no way to distinguish those two, so that's why we're really worried about things like our communication channel. Our communication channel might be doing some of that scrambling itself. We always have to assume that there's going to be some error in the system. It's impossible to make it so there's absolutely, you know, the mathematical 0 error. So yeah, if our system itself is just too noisy, we might think there's an eavesdropper and give up a key that wasn't being eavesdropped on. So yeah, that's why we need to make sure that the system noise itself is already very small so that we can attribute any additional error to eavesdroppers or give us some wiggle room for eavesdroppers. Notably, like if there's a little bit of error, we can do error correction to get rid of it. It's only when we get above around 10% error that the eavesdropper has enough information that we have to throw away the whole thing. So if we keep our system error into the few percent range, we can still generate secure key. Is there any relation between laser and quantum telecommunications? Yeah, they use a lot of the same tools like optical fiber. So advances in one tend to result in advances for the other as well. A lot of people using laser, a lot of people using like optical fiber telecommunications. So a lot of people doing quantum communications are really just taking tools directly from laser telecommunications. Okay. So I'll move on to the second part. I'll come back to other questions later at the end. Oh, just need a quick drink. All right, so the second thing I want to talk about is quantum sensors. So how we're able to use quantum information theory to kind of sense things about the world. So like I said before, we're kind of very far away from a perfect quantum computer. And there's a lot of things that make it difficult, but 3 big problems that make quantum computing incredibly difficult is that when I have these quantum systems, when I have these electron spins, when I have these superconducting circuits, when I have these trapped ions, they're very sensitive to external effects. So if you've heard about the problem of decoherence, this is the idea. It's the environment is hot and noisy, and that's going to influence my nice, perfect quantum system. Additionally, the signals that come out of these are generally very weak. And if we want to make these well, we need to design incredibly precise, selective and discriminatory devices. That means that it responds to the signals that I send it and doesn't respond to everything else. So I want to make sure that when I shine light on it, it does exactly what I want. But when nature by accident shines light on it, it better ignore it. And that's not always an easy problem to solve. Let's flip this around. What do we want out of a sensing device? Something that is able to tell us something about the environment. We want extreme sensitivity to weak signals with high selectivity and discrimination. We want to be able to tell us about what we want to know and ignore what we don't want it to know. So there's kind of a natural link here between what makes quantum computing difficult and what we want out of a sensor. So as we build tools for quantum computing, we're also building tools for quantum sensing. So in terms of a quantum information, let's also think about what we want out of a sensor. So a sensor in general is something that's using a probe to extract information about the world. So let's think about a meat thermometer. The desired information you want is the temperature inside the meat. Unfortunately, you're not able to directly measure that. The turkey is not just going to tell you what temperature it is. You need some kind of probe. So the probe we're going to send in is the metal rod. And the information that rod is going to give us is how much it expands. So by measuring the expansion of the rod, we infer the temperature of the meat. So in a quantum sense, we're going to do the exact same thing, except our sensor is going to be a quantum system. So the system is still going to be that turkey. We want to know information about this turkey. We're going to send in a quantum probe. So instead of a metal rod, we're going to send in an electron or a photon or some kind of quantum system. And what we're going to read out depends on what quantum measurement we make. So a big part of quantum sensing, a big part of kind of building different kinds of quantum sensors is choosing what measurement to make. So this is going to be a very, very broad overview. I'm not going to get into it because quantum sensors is an incredibly broad field. It's in some sense an incredibly old field, and it's in some other ways a very, very new field. It's in many ways a very, very old field. So in order to kind of just talk about what are some things you can do using quantum mechanics for sensing, I'm going to break things down to three very, very crude categories. I apologize to any scientists out there who I slot into quite the wrong category, because even these things that I'm talking about, they contain multitudes. But just to give us a very, very broad overview, I'm going to talk about quantum sensors in 3 different ways. So the first type of quantum sensor is a sensor that just uses a quantum system. Oh, we got a hand.
I have a question. Which sensors are closest to commercialization?
Definitely the first 2. We'll see that some of them are already commercialized, some of them are already standard. The third case is where we're going to start talking about ones that are a bit pie in the sky. So the first one is just going to use a quantum system in general. It's going to take advantage of the fact that something is quantum to get to use as a probe or to get some information out. The second kind of sensor is going to use quantum coherence. It's going to use the idea of superposition and the idea of measurement context to get information out. The third kind of sensor, which is, as mentioned, going to be the kind of more pie in the sky version, that's going to actually use quantum entanglement to sense something about the environment. So the type 1 sensor just uses a quantum system. It's not necessarily interested in the coherence. It's not interested in superposition, but it is interested in getting information out using quantum mechanics. So this kind of sensor, despite the fact that I'm almost calling it the dumb sensor, uses a lot of very, very complex engineering to get. So an example of a quantum sensor in this sense would be a photon detector. That's going to use a quantum effect, the avalanche that occurs when a photon interacts with a p-n junction, to get information out. It's going to tell us how many photons we have. It's going to be like a Geiger counter for photons. So this is fairly old technology and would still qualify as a quantum sensor. Another example would be a scanning electron microscope, which uses the wave-particle duality of an electron to generate extremely high-resolution images. It's using a quantum property of the electron, the fact that it can be both, that fact that it has these wave-like properties, which allow us to kind of focus it down and get information out of it. Another example would be atomic force microscopy, which literally just uses like a little needle, measures a very, very small system, often a quantum mechanical scale system, and uses its deflections to measure something about its size. So these all kind of use a quantum effect to measure something, but they don't exploit any of these kind of quantum information tools that we were talking about before. to measure something. They don't exploit superposition. They don't exploit measurement context, but they still use quantum mechanical effects. And I'm sure someone could make an argument how these do use quantum information things, but on the face of it, they don't. So you might think the type 1 sensors are the old school sensors. They're the things that we've got all figured out, and that would be false. We're still finding new kinds of things to use using quantum mechanical systems that we're still building new improvements to previous technologies and new kinds of technologies as we get better and better at engineering these kinds of quantum systems. So an example came out of IQC last year, out of Michael Reimer's lab, where they were building new kinds of single photon detectors based on semiconductors in these kind of nanowires that we can kind of see on the bottom right of the screen. So that little pokey thing there, what that actually does is it's what we call a quantum dot, and it's got this silicon nanowire popping out of it, which actually guides light into it. That allows light of many different colors and from many different angles to kind of couple well into the quantum dot to give it a high efficiency as a single photon detector. The nice thing about this is it has what we call a very, very broad response. It detects light over 500 nanometers of bandwidth with like 85% efficiency, all using these kind of quantum techniques, these quantum dot systems, which are relatively new and still being studied in many, many different ways, and using these clean room techniques that are difficult to come by and being constantly improved to improve what we would consider a kind of classical application of quantum technology to detect a single photon. This has potential applications both as a quantum optician in terms of things like building QKD systems, in terms of things like measuring photon entanglement, as well as in other kind of more practical scenarios like healthcare. If I want to measure, so one thing that they do in healthcare is they, to measure how much of a dose they're getting, measure that, if they give you a drug, it's actually flowing through your whole body. They'll put some kind of agent along with the drug that they're giving you, and then measure the light that comes out from that to make sure that it's actually progressed through your whole body. Problem is, in order to do that, you're detecting very, very weak signals, often at the low photon number level. These kind of detectors are capable of detecting the right colors with high enough efficiency to be useful for these kind of tasks. So these quantum systems, while they may not be using like quantum information tools, are still being developed day by day. So type 2 quantum sensors really kind of use the idea of coherence. And maybe the most classic example of this, one that some of you might have interacted with before, is magnetic resonance imaging, which is kind of treating your body as if it's made out of all these spinning bar magnets. And what it's going to do is it's going to excite all those bar magnets, going to give them some kind of, so normally those bar magnets are just kind of floating around randomly. Some are north-south, some are south-north, and a bunch of them are just kind of hanging out. If we put yourself in a very, very large magnet, if you've ever been inside an MRI machine, that's what that giant tube is. It's a very, very large magnet. We can get some magnetization of those spins inside your body. And then if we hit them with radio frequency pulses, we can put them into superposition states and measure how long it takes them to relax down. And when they relax down, they emit light. We can measure that light and get images of our body. If we're thinking about it less in terms of 3D images and more in terms of like identifying what a substance is, by measuring how long it takes to relax down, we can measure exactly what that substance composes of. So that'd be nuclear magnetic resonance spectroscopy instead of magnetic resonance imaging, but it's all using the same kind of idea, putting these atoms that make up our body into these superposition states and measuring what happens. So we use these exact same tools when we're talking about spin quantum computing. We're using almost these exact same tools, these exact same kind of ideas for quantum computing as we use for sensing. So there are different things you can build in this that are a bit more modern. So for example, we talk about nitrogen vacancy centers in diamond. That's where we take a diamond, which is this nice ordered structure of carbon atoms. If we are able to pop out one carbon and pop in a nitrogen, that nitrogen is kind of acting as a fake atom, something that has very specific properties and can be addressed as if it was a single atom. And by manipulating its magnetic properties, we can build qubits as well as sensors. We bring that single fake atom near something that we want to measure, and based on the magnetic properties of that material, by reading the magnetic properties of the nitrogen vacancy center, we can understand something about what's happening. So in this picture here, they're showing it as it approaches like a lipid layer. And if there are things popping out of that, then they'll introduce some magnetic properties that the nitrogen vacancy center may be able to pick up. We can also think about going to kind of more of a single atom limit through nanoscale magnetic resonance imaging, where yeah, we're really kind of getting down to that level where we think about like what we're made up. We're made up of, you know, oodles of atoms. How can we measure a single atom using these techniques? And that's what some researchers are working on, both for quantum computing as well as quantum sensing. Another example of coherence that you might be familiar with is interference. So kind of a classic example of that is the double slit experiment. We shine light through a superposition of slit 1 and slit 2. We look at a pattern on the screen and we see these series of fringes, these series of light and dark fringes. If I wanted to understand what that object was, so what that double slit was, well, I just measure the spacing between the fringes and it could tell me information like how wide each slit was, how far apart those slits are. If I expand that to something like a crystal, I shine light or X-rays through a crystal and look at the interference pattern I see on the screen, I can understand things about the structure of that crystal. So these kind of interference tricks are also, I can also think about them in the exact same way as I do about measuring superposition. So in the double slit case, I put light through the 2 different slits. That's kind of my 0 and 1. 0, it goes through slit 1, 1, it goes through slit 2. I look at the screen, I'm kind of measuring which superposition state I was looking at. So I'm using those same ideas for quantum information already to do something that's classical, but kind of gets information out about something I want to know. There's a whole bunch of other different kinds of coherence-based sensors I could think about. So as we know from wave-particle duality, photons are not the only thing that interfere. Electrons, neutrons, all these kind of quantum particles can exhibit wave-like behaviors in the right scenario. So there are people working at IQC on neutron interferometry. So same idea as photon interferometry, except I'm going to put a neutron into a superposition of different paths. I'm going to put something in one of those, and then I'm going to recombine them. And then depending on the wave interference I see between the 2 different neutrons, or sorry, not 2 different neutrons, between the neutron in the superposition state, I'm going to infer properties of that object. Neutrons are going to interact with objects in a much different way than photons, so I can get much different information out. Additionally, because neutrons are heavy objects, the same way that electron microscopes can get much finer details, neutrons have an even shorter wavelength and get incredibly fine details out of them. I can also think about EEG machines, which have what's called a squid inside of them. That's a superconducting quantum interference device. So I take a circuit and I cool it down to cryogenic temperatures, and the electrons start behaving together and when they become superconducting. And now they kind of, instead of behaving like electrons bumping into each other, they all behave together coherently. And if I kind of have one electron wave going this way, one electron wave going the other, those 2 waves will cause interference. As we know, when electricity travels around a loop, it creates a magnetic field, so it can actually be used to pick up magnetic fields. And that's what these EEG machines are doing. They're using that quantum interference to measure magnetic properties of your brain using a quantum sensor. Question, yeah.
I have a question as my light came on, so there we go. Alexandra's asking, well, do type 1 and 2 sensors destroy the quantum state of the particle? Like A, is that accurate? And then B, what are the non-destructive sensing options that we have?
Yeah, that's a very good question. So from a practical point of view, they tend to. When I get to the measurement part, they destroy the quantum state of the particle. What's a good example to use for that one? Let's talk about the double slit for a second. If I want to know something about that double slit, I'm going to send it through the superposition of both slits. I'm going to look at the screen. In order to measure whether a photon was there or not, I need to detect it with something. So that's going to be a camera. When the photon gets absorbed by the camera, it's going to convert into electrons. Those electrons are going to convert into something that my computer can read. And by that point, the quantum state is destroyed. There are other ways to make non-destructive measurements. We'll touch on it briefly in type 3 sensors. Those usually involve another quantum state coming to measure something about that quantum state and then leaving. But even then, whenever I measure quantum state, I'm collapsing the wave function, if you want to use that word. I'm destroying the quantum information in the system. but I can think about schemes where I measure the property that I want, but don't actually destroy the particle. So say I measure the position of the photon, so I destroy its momentum information, but I don't actually destroy the photon. These are very, tend to be complicated to do, and like people who study these kind of things, it's still very much a research topic rather than a practical thing that people do. But yeah. Oh, and just to make sure, like, for example, NMR machines, when I take an MRI image of your body, I don't destroy your whole body. So, I mean, those atoms that you're still built up of are still there, but I do kind of collapse their quantum state. So I always have my head in photons because I'm a laser guy, which always do get destroyed, but that's not necessarily the case for some that are more matter-based.
Well, I had an MRI from a boxing injury, but I think I'm still here. So great. Glad you're not shooting your photon rays. Pawan Kumar had an insight too that they were performing Michelson-Morley's experiment in an advanced physics lab and used scanning electron microscope for analyzation of graphene for a small research project.
Yeah, well, that's cool. Yeah, no, the scanning electron microscopes are one of the kind of the earlier they get used a lot. So you can, they're very expensive. They're very neat. But yeah, if you get a chance to look up some SEM images when you have some time, they're amazing. All right. So one more type, and this is where I'm going to talk a bit about what I did work on back when I was studying optics. One of the important things here is you choose how you measure your quantum state. So in the double slit experiment, if I wanted to know which slit it went through, I could have just shone light on it and just measured it right away after the slits, built that up on my camera and get some information out. But by looking at those interference fringes, by choosing to measure the superposition, I get different kinds of information out. I get that information out in a different form. And not all of these forms are created equal. So let's look at these three images here. So what we see here is you see those black dashed lines. So those are two underlying distributions. Think about it like light coming from a faraway star. So I have my two stars, and the light that comes from them, it overlaps by a lot. So if I look at my camera that's measuring photon by photon, I see these red graphs here. They look noisy as I'm measuring each photon. It kind of looks like garbage. But as they get very close together, it's very difficult for me to infer information such as how far apart were those stars to begin with. That's because I'm choosing to measure just that distribution. I'm choosing to put a camera there and measure the distribution that comes out. But if I use some of these insights of quantum superposition and quantum information measurements and make different kinds of measurements, so instead of putting a camera there and measuring the intensity, I measured different superposition states, which are actually shown as these orange curves on the bottom there. If I make measurements in that way instead, I can actually get this information out much more efficiently. So I get very limited information by doing what I might think of as a standard thing, just looking at what I see. But I get very delicate information, very useful information by measuring in different quantum states. So in this case, we're using kind of a quantum technique for measuring non-quantum data, but it allows us to get more information out per photon. So that's often what we get out of quantum metrology, is not so much information that we would not have been able to use before, but we get the information out more efficiently. Each photon gives us more information than it would have otherwise. All right, and now very briefly, because this is, once again, like the pie in the sky version, there is kind of like a third type of quantum sensor, which really is like the heart of quantum sensing, which is where you're using quantum properties of the state. So an example of this would be when you use entangled states. An example of that would be, say, for quantum error correction. If you've looked at quantum error correction from a quantum computing perspective before, you've seen that if I have many qubits that all work together, they can protect a quantum computation from error by acting as one large logical qubit. I can use the same kind of things to build better quantum sensors, things that protect them against certain types of noise to make sure I get the information that I want out by using many qubits acting together to get a bit of information out, but a useful bit of information out. For example, I can also use entangled states like these noon states here. where they're able to, so a noon state is basically a superposition of a bunch of photons and no photons, sorry, like many photons here and no photons here, or many photons here and no photons here. And that state can actually see interference fringes that oscillate much more quickly than if I had one photon here or one photon here. So by using that kind of delicate entangled state, I can get information out much more efficiently. We can also start talking about squeeze states of light. So once again, going back to Heisenberg's uncertainty principle, the more I know about position, the less I know about momentum. So if I sacrifice some of my knowledge about position, so if I say I don't know anything about position, I can know momentum very certainly. In a squeeze state of light, what we're effectively doing is we're sacrificing information about something in order to get information about something else. We make something very uncertain to get information about something else. An example here is these kind of interference fringes. So normally if I look at how light interacts with other light, if I put them into an interferometer, I'm going to see some kind of interference fringes that go up and down. But if I'm really interested in low photon number stuff, there's going to be some air there, that kind of blue fuzziness to it. If I send in a squeeze state of light, I can control where that fuzziness shows up. So it might be really fuzzy in certain areas, but get really, really narrow, really, really certain in others. And by controlling where I get that certainty, I can perhaps get an advantage. And this kind of tool is actually being used in the next generation of the LIGO Gravitational Wave Observatory in order to make sure that they have as low noise as possible by introducing these kind of quantum states. You can also think about other neat things like quantum noise radar, where I send out entangled quantum states and recombine them together in order to do some kind of entangling measurement that gives me information about what one of the photons did interact with. And by using entangling measurements, by using entangled states, I can sometimes get more information than I would have otherwise. All right, this is my last slide, I promise. So oftentimes physicists just come up with stuff. And basically, as a physicist, I can attest to this, we're very, very comfortable with physics, and we're not often comfortable with how to actually build things that do a thing. So what's kind of happened as quantum information has become more popular, and especially kind of in the early days of it, was people would come up with this awesome new quantum tool that they could use as a quantum sensor, and then realize that there was a tool that they could build instead that didn't use any quantum physics, but did the exact same thing. So an example was ghost imaging, where we would image something about an object without ever interacting with it, which was this really cool thing that seemed to be, using something about entanglement, but really was only using correlation. It wasn't using quantum correlation, it was just using correlation. So I could build the exact same thing using a laser and something that imparts different shapes onto the laser beam that I control. However, I might not have thought about that classical technique if I didn't first think about the quantum technique. Another example is quantum optical coherence tomography. That's where I'm able to measure something about a sample and in such a way that the entanglement actually cancels out the spreading that I would get. So if I send a pulse of light through a piece of glass, it's going to spread out. But if I send an entangled light and send half of it through the glass, half of it not through the glass, I can actually cancel out that dispersion to a large degree, which sounds awesome. But once again, you're not actually using the quantum correlation there, you're only using the classical correlation. So by building up your laser pulses in the right way, you can get the exact same effect with like a millionfold signal improvement. But you're taking that inspiration from the quantum mechanical solution. So these kind of quantum inspired sensors also serve a role. So thinking about not just how we can build quantum sensors, but when we have a quantum sensor, can we do it without quantum? Can we use inspiration from that quantum side to build something new? Is also useful. If you've been following quantum computing news, you might have seen this kind of thing also holds up for algorithms. So I believe the famous one was the Netflix algorithm, the recommendation algorithm based on quantum mechanics, which someone then came around and said, oh, we can actually do this classically, but used inspiration from that existing quantum algorithm to come up with a new classical algorithm. So, there can be a two-way flow of information there. So when we talk about quantum sensors, the tools that we build for quantum computing are not useful just for computing. We can use these ideas to build power-effect technologies for sensing, metrology, and imaging. And by taking inspiration from them, we can develop new classical techniques inspired by their quantum equivalents. So that's all I have to say. So once again, I'm coming from the Institute for Quantum Computing. We have a variety of educational programs. So for anyone joining who's a high school student, I recommend checking out the Quantum Cryptography School for young students. Anyone in undergraduate, I recommend checking out the Undergraduate School on Experimental Quantum Information Processing. Anyone who happens to be a high school teacher, we run PD workshops called Schrodinger's Class for grade 11 and 12 science teachers from across Canada and around the world. They're all open to international applicants. You can find more information on iqc.ca. And with that, I'd like to thank you all for your time.
Oh, wait, there's more. So we have a bunch of questions and really great interaction. Thank you, people. It's easier for us to parse the questions if you put them in the Q&A rather than the chat, but we're going through, and one is, where is optical coherence tomography used?
Optical coherence tomography is already used as a tool in medical imaging. So quantum optical coherence tomography is what it sounds like. It's someone tacked the word quantum in front of optical coherence tomography, which is a way to image some kind of system, whether or not it's for a medical purpose or for a diagnostic purpose or for just imaging what something is. So I'm trying to think of a very, very specific example where it's used a lot. I know it's used a lot in the medical sector. I don't have a good specific oh, you've probably seen it if you've been in this box the same way that I have for the MRI machine, but it is a commonly used approach. What the quantum part of it did was kind of introduce a way to reduce the spreading that happens when a pulse of light travels through a dispersive medium, something that stretches out the pulse, which would allow us to get better timing resolution, which would allow us to get better information out. But turns out there's ways to do that just using classical techniques.
Ping had a question earlier, and I'm just getting back to it. Is there a QKD algorithm that doesn't suffer the denial of service attack?
I don't think so. I think the denial of service attack is something, I haven't heard of one at least. Denial of service attack is something you can always do. If I'm measuring there, I can always deny the, if I'm measuring, I can always interrupt the service. The important thing there is that in these cases, it's not always the end of the world. If your service is denied, it is the end of the world if you use a key that you think is secure that turns out to be compromised. So denial of service is bad. Using a compromised key, catastrophe. So it's balancing those two. And I mean, even classical communication, I could deny your service by just cutting your cord. So,
don't cut my cord.
I'd rather not, but
thanks. Well, good thing you're down the highway a bit. Constantina asked, how does Samsung Galaxy quantum processor work? From what I understand, not a physicist, a qubit's supposed to travel to truly give a random number. However, if you know the wave function, you can know the possibilities for the result.
So I don't know about this Samsung Galaxy quantum processor. If I were to guess, I'm going to guess that that's one of these cases where they kind of threw the word quantum on there, but it's not. It's definitely not actually a quantum computer. But it probably is just. It's the same way that Duracell quantum batteries. They just throw the word quantum on there because it's fun. But in terms of the deeper question there about the randomness, yes, when I make a superposition state, I do know the possibilities, but I don't know which one I'm going to get out. The same way that when I flip a coin, I know it's going to be either heads or tails, but I don't know which one's it's going to be until I actually look at the coin. So I know the possibilities going in, assuming that I've calibrated my system very well, I know the exact probabilities, but I don't actually know what it's going to be until I actually do the experiment. So this is why we can use this to generate truly random numbers, because even as the experimentalist who sets everything up, I don't know what it's going to be until I actually do the experiment. And yeah, I don't know about the Samsung one in particular, but there are quantum random number generators that you can buy that use quantum mechanics to actually generate random numbers.
Goodness gracious, there are amazing questions. So I'm looking at the time, it's 1:04. So we've got a little bit more going on in terms of time. however, do join our association. And here's one. Dave De Silva is working with Harvard University Center for the Environment, a PhD fellow looking to deploy quantum computing in support of making the world, for sure, air quality better. Would you please give words of encouragement?
Go for it. So I know that a lot of, so in terms of quantum computing for the environment, kind of the biggest thing that comes up is really the quantum simulation aspect. So for example, simulating how nitrogen fixation works. This is something that modern quantum computers can't really touch, but if we want to start understanding how future quantum computers might be useful for it, we need people thinking about that early on, so that when the hardware catches up, the software is kind of there to meet it. So, I mean, that's a fantastic project, I think.
Based on all those different types of sensors, in your view, will it open ways for new types of quantum computers? Which area is more advanced, the qubits or the sensors?
I'd say they really go hand in hand. I mean, so the sensors, like in a sense, we're using quantum sensors all the time already. Like things like MRI machines, things like different kinds of cameras that we use are all based on quantum effects. So if you were to say which fields has come further, well, sensors are currently deployed, so they're already a thing. But in terms of like how we're going to build these up, it's going to be really kind of a back and forth. One thing when people talk about quantum computing, I find, is that it's kind of, you know, what's actually going to build the quantum computer? Is it going to be superconducting circuits? Is it going to be trapped ions? Is it going to be photons? The same way that like all computers today are really based out of semiconductor transistors. And I don't know what the future quantum computers are going to be built of, but I do know that like each of these different kinds of tools is going to be useful for different things. Even if we don't end up building full-scale quantum computers out of photons, the sensing technology that we build from understanding quantum computation with photons will be useful. So yeah, people talk about different quantum computing platforms as, oh, you're betting on a losing horse, so you're going to get new, interesting research out of it either way.
Cool. Which companies in the world are designing quantum chips, and how can they enhance devices based on your research?
Well, I don't do too much research myself into quantum chips. I don't, that's, the details of that go a bit above me. There are a lot of people in Waterloo, in Toronto, in Canada, around the world who are much, much more suited to that and do amazing things. In terms of groups that are actually working on quantum chips, like there's a lot of academic groups working on it, including many at IQC, many at Waterloo. In terms of companies, probably most famously would be Google, IBM, and Rigetti. We're probably the big three, and they're working on quantum circuits for quantum computation. They're not the only three, but they'd probably be considered the big three.
Can you speak about radar, quantum radar, and the RSA algorithm? A few people would like you to elaborate on that.
Sure. So the RSA algorithm, there's a lot of documentation out there with Google, and I'm not a cryptographer, so I won't go too deep into it. The basic idea is you have a private key. Sorry, the bank has a private key and you have a public key. So they give everyone a public key that they use to encrypt the data, but it can only be unlocked with their private key. Your public key, think about your public key as if it was two numbers multiplied together. And the only way to unlock the safe is if you know those two numbers. So the bank knows those two numbers, you know the two numbers multiplied together, so you can encrypt, but you can't decrypt unless you know those two numbers multiplied together. Since the bank knows that, they can unlock it, but if someone else tries to come along, they basically have to solve the factoring problem, and that's very difficult computationally to do. It's a very hand-wavy, but there's a lot of stuff online about the kind of guts of how RSA works. In terms of quantum radar, there's a few different competing things there, but when I'm talking about the type 3 sensor there, what I'm really talking about is something called quantum illumination. I believe it's about a 5-year-old paper now from Seth Lloyd. The idea is that I have entangled photon pairs. I send them out. I have one of them interact with an object, and then I combine them back together. So I measure reflections from an object, and then I re-interfere my two entangled photons. And by making a specific a specific measurement on those entangled photons, I can actually cancel out a lot of the different background noise. I can get a much higher signal to noise ratio than I get with classical techniques. But I can also kind of circumvent this by just shining brighter light at the object. So this really isn't for scenarios where I'm interested in just shining brighter light. This might be interested in scenarios where I'm worried about stealth, where I want to send as little light as humanly possible. Those kind of scenarios. So it's not for every scenario even. It's not saying it's going to replace radar, but it might be useful in certain scenarios. And that's really, from a physics perspective, I'm just more interested in the fact that it actually does a thing.
Does D-Wave actually have a quantum computer like they claim they do?
I'm not going to step on that one. I know when to lean back and just keep my mouth shut, so I'm not going to say anything on that.
Sweet. We'll move on then. What is that? Kenny Rogers, know when to hold them, know when to fold them. What do you think about the new BEC results from NASA on the ISS today?
Ooh, I actually didn't see those today. I'm a very last minute person, so I was working on the slides this morning. I was able to check in the news. I'm gonna have to go look at those later.
It's okay, or Will, if you want to elaborate, we can do that.
I don't know much about that.
Ghost sensing versus single pixel cameras.
Yeah. So ghost imaging, the reason they call it ghost imaging is that you're measuring an image that the photon that you measured never really interacted with. So when I generate these entangled photons, they share these strong correlations. So if I measure one photon here, the other photon's going to be here. Measure it here, the other one's here. Measure it here, the other one's here, for example. So if I have this photon interact with an object, and then just measure whether or not it made it through the object or not. I'm not measuring where it hit the object, I'm just measuring, did it get through? And now I measure, when it did get through, where do I see the photon? Then the map that I measure there will be the same as the image that I see over here. Yeah, so that's the idea. The problem there is that really all I'm doing is using the correlations between photon 1 and photon 2. I can easily generate those correlations using some kind of other method. So say instead of using entangled photons, I'm just going to move both lasers at the same rate. And I can still kind of do almost the same thing. So instead I have two strong laser beams instead of two very, very weak single photons. So I can get almost the same advantage. The single pixel camera idea kind of folds that into one beam by instead of having two beams that move the same, it has one beam, but I kind of like shape it in different ways so that the shape of the beam kind of takes the place of the resolved camera here, and whether I detect it or not takes the place, which is that single pixel, takes the place of that kind of bucket detector on the other side. This same idea of imposing correlations.
Super cool. I don't know if you can stay on for a bit. I certainly can, but I do know that we've got just about a minute and a half. I was looking at where people said that they were coming from. So we have Brazil, Perth, Australia, where it's after midnight there. Islamabad, Pakistan, I think it's pretty late there too. Romania/Germany, also Germany. Ottawa, San Diego, Montreal. I guess if someone's with Harvard, maybe they're in Boston. Obviously Waterloo and Toronto. So I just want to thank everyone for joining, and really, like, this community is growing exponentially. Bring your friends, sign up for our newsletter where you'll get a lot of information about what we're doing. Also, if you have a sponsor, and it could be $2 that you may have in your, I guess not pocket, but like bank account, send it through the secure channel to the bank. We're a nonprofit. And so what we're trying to do is things like create educational material, get information out there, maybe even run some hackathons, and bringing together all people in our community and also our world. And this call, you all are a great example of that. So if you could sponsor us, if you know someone who could sponsor us, or both, we'd really appreciate it. We want to try to do a lot more outreach. as we heard from Dr. John today, there's so much potential. You can fry an egg backwards. Your car, you can have the magic sauce, so your car can go forward and backwards at the same time. Look what I've learned. A supercomputer can have a squid in it. And what was the other one? Oh, quantum dot silicone nanowire. You can use quantum optics in healthcare, and you can get an MRI where your body is not torn apart. Look, I'm right here. So this is just what we're glimpsing. I think as we're seeing this moment of change in our world, we bring it to quantum information, and there's so much possibility. So yeah, if there were a few artists on this call, actually, we need artists. We need people who can create and innovate. We need scientists and engineers, everybody to say, okay, what's a problem we can solve? And can we do it with this? Climate change and climate science, absolutely. Let's really bring our minds together, because there's so many great things we can do in the world. And it starts with all you all. That's my Kentucky, all you all on the call. So thank you. Dr. John, did you have any last things? You want to stay on for a couple more questions?
I can stay on for a couple more, but yeah, no, thank you all very much for letting me ramble. That was great.
I think it was helpful. So here's one. I want to ask this: agreement or disagreement on measurements rely on classical communications, right? So what if this channel becomes hacked?
Agreement or, I see. Agreement or disagreement on classical measurements relies on classical communication. Yes, but that classical communication can be public. Like when they say whether or not they agree or not, it doesn't matter if someone's listening in or not. If anyone collects that information, that's fine. They can, as far as Alice and Bob are concerned, they can just yell at each other with a megaphone. If someone gets that information, they're not getting any information about the key. They're getting information about how Alice and Bob measured, but they're not getting information about what Alice and Bob measured. So that's the difference between how and what. But yeah, it's fine if someone listens in. If someone else controls it, they might destroy the key. But I'd have to think about that one a bit more, but I think that would be equivalent to denial of service, because then they'll pick that up in the error correction step.
The next call is June 24th. And how quantum computing has changed electronics and power or control engineering. How has quantum computing changed electronics and power or control engineering?
I don't know if I have an answer to that. I mean, a lot of the technologies that we build, like today in general, rely on quantum mechanics in a roundabout way. Like, I can't think of any quantum information applications there. But you know, I mean, everything today uses semiconductors or uses lasers in some way. I don't know enough about that field to make a clear answer on that, though.
We have lots of questions. I don't think we're going to get to them all. Here's one last one. Is it being applied in pathology identification?
I'm not sure. I don't know of any particular examples. I mean, so I just don't know enough about pathology, to be honest, but I do know that there's different research in terms of different ways that I can identify diseases, different ways that I can identify like how I discriminate between healthy and non-healthy cells using quantum information ideas, where the idea is I'm going to use I'm going to use a standard technology like NMR and change how I interact with molecules to get different information out. So I'm able to tell apart a cancerous cell from just a fatty cell, for example, in specific scenarios. So coming up with those specific sequences and those specific kinds of tools to make that discriminating measurement, that's very active research. I have heard from some groups of different promising ways to do that use these kind of quantum techniques. I don't know of any that are in active use right now, but yeah, there's promise there for sure.
Awesome. I think we're going to close it out now and say thank you so much. You've opened my eyes to a world of possibility, and we've got a great community. I did forget Esperanza in Madrid. There's probably lots of other people, but what a great time to come together. Good way for us, at least in Canada, to spend our lunch hour. Dr. John, thank you. And thank all of you for joining. We really appreciate it.
Oh, thank you very much.
So sign up for the newsletter. You'll get the recording. You'll find out about our next calls, and have a great day, evening, morning, wherever you are in the world.